Good morning, everyone, and welcome to the second day of the web conference. Can everybody hear me? Cool. So yeah, we have a great program today as well. The schedule follows a pretty similar pattern to yesterday. We have two sessions of oral presentations, and then two poster sessions, and a plenary panel in the afternoon that you don't want to miss. So we welcome you to all of that good material. But we're starting this morning with a keynote that I'm very happy to have from Alistair Moffat. So Alistair is a professor and has been a faculty member in the University of Melbourne in the past 40 years. His early work focused on index compression, and more recently he has focused on information retrieval evaluation, including topics such as user query formulation and result perusal, and rank biased measurement, a topic that he will touch upon in his talk today. He was inducted to the SIG-IR Academy in 2021 and is an ACM fellow recognized for his contribution to the implementation and evaluation of search systems. And before giving Alistair the stage, I just want to encourage everyone to ask questions. We will allow this in the end, but also you have an option through the platform. If you are out of full screen mode, you have buttons on the right. Just type your questions. I will track this and we will have your questions in the end. So please feel free to participate. And with that, Alistair, the stage is yours.
Great, thank you. So hopefully this is all going to work. It's kind of intimidating to be doing Zoom presentation without being able to see what's going on in the audience and without seeing where the yawns and the sleepy eyes are. But maybe there's people out there listening, and maybe I'm not just sitting by a room in Melbourne and it's all just a practical joke, I hope. Apologies for the slightly pretentious title, Everything You Never Knew You Needed to Know About Rank Biased Measurement in Web Search. I've got another option on that title to show you later in the talk or at the end of the talk that has a different mix of existential and universal quantification, and the logicians amongst you can argue about which one is more correct and which one is the truth for what I've delivered to you personally. So what I'm going to do is tell you a story. Like all good stories, it starts with once upon a time, and then it's got some plot development over a sequence of chapters, and then it ends with a surprise at the end. And the surprise isn't anything particularly surprising, but I have to pretend that it's going to be a surprise, but it is new. So here we go. Let's tell a story. And the story goes once upon a time. So a long time ago in the 70s and 80s, when we did IR experiments, we had Boolean retrieval systems. And what we did was we ran a system against a collection of documents, and we got an answer set. And then we had to somehow measure the quality of that answer set against some kind of a reference system. And I'm going to use these two words consistently. I'm going to have a reference, which is what I've got as what I think of as being my goal of the experiment. And I'm going to have systems that generate observations. And I'm going to talk always about observations versus references. The observations are always going to be called B, and the references are always going to be called R. And in the once upon a time world, the observations, the B, was an order agnostic set of objects drawn from some domain because we were doing Boolean queries. And the reference, the thing that we were testing against, the thing that we were regarding as our objective, our goal, was also a set. And so we had a picture like this. And I'm sure you've all seen this picture in a textbook or in an IR lecture from when you were younger. And maybe some of you have even delivered this picture in IR lectures. And maybe there's someone out there who's even done it this week. I don't know. So this is the once upon a time situation where we have an observation B, which is a set. We have a reference R, which is a set, and we're trying to assess the quality of the system that led to the observation. So the reference is common across systems. The observation comes from a particular system. And we all know what I'm going to do next. I'm going to tell you about precision. So I'm not going to talk very long about precision. Precision is essentially the fraction of the observation that's interesting. And this is the standard way that we write precision, except that I'm writing it as B given R, right? We've got an observation and we want to score for that observation given the reference, which is why I'm using that notation. And then I'm also going to use slightly different notation to express the precision. The denominator is the same here, the B is the same, but I'm using a C-like notation here. So that's going to be 0 if B of I is a member of R, and it's going to be 1 if B of I is, it's going to be 1 if B of I is a member of R, and it's going to be 0 if it's not. And we're going to work out that ratio. So there's precision. You're all familiar with that. I don't have to dwell on that. Similarly, we have recall. Here's what recall looks like. It's a reflection. It's the fraction of the things that we want that actually made it into the observation set. And then out of that, we have this nice symmetry. We have this duality that precision of B given R is equal to recall of R given B. Okay, and I'm sure everyone's familiar with this, and I don't think I'm telling you anything new yet. This is what I'm calling a set given set measurement. So we've got this notion of both of the things are sets. And so we've got a measurement regime where the observation is a set and we're quantifying its usefulness against a reference that's also a set. Please bear that in mind, because we're now moving on to chapter 1 or chapter 2, depending on where we start the counting. And I'm going to start talking about what happened in the 1990s with information retrieval. So what happened was that we started getting similarity scoring going on. We had TF-IDF mechanisms. We had the computational power to be able to use them, and that's something that often gets overlooked. It's not that the methods hadn't been invented. We just didn't have the computational power to use them sensibly. And in this world, the observation became an ordered ranking, which I'm sure we're all familiar with, the 10 blue links or the 100 blue links, whatever it is you're going to get. And we have a sense where the first element's more important than the 10th or the 100th. So it definitely has an order relation on it. But we still had relevance judgments that were an unordered set. So the picture now looks like this. We've got the observation, my brown thing. The observation is a ranking, and I'm using arrows to represent rankings here. The reference is the same curials we've always had. It's a set of relevant documents. And so we've got this problem now in terms of what we want to measure. We've got a ranking given set measurement environment. So what did we do? Well, in the early 1990s, we said, oh, gee, I don't know what to do. So let's measure precision at 5. Oh, and maybe measure precision at 10 as well. Maybe even measure precision at 20 as well. And maybe we'll measure precision at 100 as well. And then you got 2 more choices. You can either build an enormous table, which has got columns for precision at 5 and columns for precision at 10, or you do what humans love to do. We take things that we shouldn't really average and we compute an average across them. So we could, for example, get a single number out by averaging things across in the way I've shown it here. I'm averaging across depths, or we could average across recall levels, and the ultimate guide to recall levels is where the relevant documents are. And so if you average across where the relevant documents are, you can end up with average precision. And I'm sure you all know that as well. I'm not onto anything that none of you don't know yet, if I've got my quantifications correct. And that's all I'm going to say about average precision. The next part of the story is in SIGIR 2000 in Athens, where Cal Javelin and Jana Kekalainen gave us this paper. They're talking about retrieving highly relevant documents, but the key part of this paper is discounted cumulative gain, which we all know of as DCG. And DCG looks like this. So what we've got is an observation, which is a ranking, and a reference, which is a set. And so what we're doing, we're computing the presence or absence of the items in the ranking, whether or not they're in the set, and we're discounting. This is the discount. And the discount in DCG is by log to the base 2 of 1 plus I, which is, well, log is a very slowly growing function, so 1 over log to the base 2 of 1 plus I is a very slowly decreasing function. And they said, oh, why don't we just use this? This will be top focus, so we get more emphasis on the top, and we don't have to do that averaging over precision levels thing that we were doing until now. And this is the story of the 2000s. Unfortunately, this function is not bounded in the sum. That keeps on growing. I mean, log grows slowly, 1 over log decreases slowly, and the sum of 1 over log is unbounded. So if we want to actually have numbers that we compare, we have to have some kind of a depth parameter. And so suddenly it's become more complicated again, because we're now saying, gee, we have to work out DCG at some depth. And then we have to be careful that we don't overrun the ranking that we've got. So it starts becoming a bit messy. And also, why 1 over log? What's the basis for 1 over log? Why is that an interesting function at all? And in the paper, this is a screenshot out of the paper, the statement was, by selecting the base of the logarithm, sharper or smoother discounts can be computed to model varying user behavior. And that's not actually true. I haven't ever tried arguing this with Cal, but one day I'll be brave enough to give this a go. Because logs are all multiplicatively related. And so whatever base you choose for the log, you get, roughly speaking, the same ratios between different values. Okay, so this is actually a fixed scheme. It's not varying according to the user. That work got published further with extensions and tours in 2002. Here's the paper, Cumulative Gain-Based Evaluation, because by this stage they'd recognized that the actual mechanism was what the interesting part of this work was, and to retrieve highly relevant documents was as a bit of a distraction. So this is normalized DCG, NDCG, where there's a scaling process used to bring it into range. An alternative scaling process in NDCG, as I'm sure you know, the scaling process is according to the ideal DCG, which is saying, oh, well, look, put all of the most relevant documents first in the ranking, and then work through the relevance grades until you've got all of them in the ranking, and that gives you the best possible ranking you can get for that query. The problem with that is that you have to know all of the QRELs, and you have to say, well, this is query specific now, and if we do some more judgments and find some more relevant documents, all the scores have to change, and they might go up or they might go down. A different way of normalizing DCG is to simply say, well, what's the maximum denominator that we could get to bring it back into the range 0 to 1? And it's simply the sum of the 1 over logs of the 1 plus i's. And so this is a differently normalized one that I call scaled discount cumulative gain. It's another way of thinking about it is that it's a globally normalized DCG. And all of that brings me to this important graph. So you're going to see several of these graphs. So I am going to take this first one quite slowly. What I've got here is 3 different sets of parameters. So we've got 10 to the 3, 10 to the 5, and 10 to the 7 going on here. And for each of those parameters, I've got 2 curves showing. The one that's decreasing, here's the red one going down here that I'm tracing with my pen. Hopefully you can see that. That one there that I just traced, that's the weights attached to the ranks. So we've got depths here. This is depth in the ranking across the bottom axis. And that's the weights attached to the depth. So you can see that over this log scale on the vertical axis, if I have DCG or SDCG at depth 1,000 with a parameter D of 1,000, the weights change. At the top, the weight is a little bit below 10 to the minus 2. And at the bottom, down at depth 1,000, the weight is a little bit below 10 to the minus 3. So the weights actually decrease pretty slowly. Then the other line in each pair is a line that shows the cumulative sum. So the cumulative sums are going to add up to 1 because we're computing that. So in the end, we're going to get to, we know everything. 10 to the power of 0 is 1, right? So this is where we know everything about the measurement. And the problem with DCG is that this line that I've sketched, the climbing line, it grows very slowly. We have to have a lot of relevance judgments before we actually have confidence in the score. That's a very important point that I'm going to come back to a number of times. So if I now sketch a different way, between 1 and down to the cumulative line, that's all uncertainty in the score. If I've only got 10 documents judged, the first 10 documents judged, well, I've got more than 9/10 of the score range is unaccounted for by known information, and I haven't measured anything at all. So we have to be a bit careful. We have to know what it is we're measuring, and the situation only gets worse if I go to deeper depths. And of course, no one's seriously going to do DCG at 10,000 or DCG at 10 million, but nevertheless, I'm showing you these graphs, and we're going to compare them to some other graphs in just a few minutes. The next part of the story involves this map. SIGAR 2005 was in Salvador in Brazil, and maybe there's people in the audience who attended. And this is the flights from Melbourne to Auckland, Auckland to, whoops, I missed Santiago, Santiago to Sao Paulo, and then Sao Paulo to Salvador in Brazil. That's the flight route that Justin Zobel and I took to get there. I can't remember how many hours it was. It was like 24 or 28 hours or something of flying. And we were on the same plane and we sat next to each other, perhaps a mistake, but we sat next to each other and spent some of the time annoying each other by just being ourselves, and some of the time talking about evaluation. So the next part of the story is a thing called rank biased precision, and here's the first of my rank biased words. And this was published in TUIS in 2008 after being developed on those flights. And then the paper got started being written on the flights back. We were programming and starting to write the paper on the flights back from SIGAR 2005. And then it took 3 years for us to actually get it published. And most of the time wasted was our fault because we were a bit slow doing some revisions and didn't want to have to argue with referees. You know how it is, the dreaded argument with the referees. Rank bias precision. So it's the same kind of weighting scheme, the critical difference being that we used the geometric distribution, which has got a normalizing factor there. So that's what I had a minute ago. The second one is the weighting scheme. It's the same thing. I'm saying, is the element in the ranking in the set we're interested in? Compared to DCG, this has two huge differences because we've got a converging sum, and I'll give you an example in just a minute to show you why I think that's important, and a user behavior model. We could argue for this. We could say this makes sense as a weighting function because, and here's the because I want to show you. This is a screenshot from the original paper. Except that in the original paper, we were silly enough to use P as a parameter, and we're actually now realized that P is heavily overloaded. So now we talk about phi as the parameter. So I've pasted phi on top of the P's in this picture from the original paper. And the way to think about this is that let's talk about one user consuming a ranking first. The assumption is that they get given a ranking back from a search service, and they view the first item in the rank list. So I'm entering the diagram here. They view the first item in the rank list, and they either accrue some gain out of it, or they don't. It's either relevant or it's not. And if they accrue some gain, well, they get the benefit of that, and then they make a decision. They either go on to the next document in the list with probability phi, or they exit the ranking with probability 1 minus phi. And if they exit the ranking, they finish the search and they pay the search cost. Now, what is the search cost, you're asking yourself? Well, the search cost was their time. They spent some time looking down the list to say, hey, are we there yet? Are we there yet? Have I found what I'm looking for yet? Have I got enough satisfaction or enough utility yet? And in this simple model of user behavior, It's always proceeding with probability phi. So we've got, go around the loop and do it again with probability phi. And at every point, it's exit with probability 1 minus phi. So this simple model of possible user behavior as they consume the ranked list, you then say, okay, well, that's one person. What happens if we've got 1 million people or 1 billion people or an infinite number of people? So you end up with a probability distribution, of course. So out of the geometric distribution, you can say, what's the expectation across an infinity of users who have this particular type of behavior? And that's what I meant by the huge step forward in thinking about evaluation. And I want to give you an example. I'm going to be a little bit apologetic. I'm going to work through this because there's another thing about rank bias precision that's, in my experience, widely understood, widely misunderstood, and worth dwelling on. So here's an example ranking. I'm pretending I've got document number 7, document number 4, document number 11, and so on. And here's an example reference. So the observation is the ranking that came out of a system. The reference is our standard, our QRELs, our hoped for answer. And what we are going to do is to compute an RBP score. If we're going to compute an RBP score, we have to choose a parameter. And in this particular example, I'm going to go through and use the parameter 0.8. So we're saying 80% at each step, 80% of the users will go ahead and look at another document, and 20% of them will say, oh, I've seen enough. I can't be bothered continuing. So we're going to lose users as we go down the ranking. And what's going to happen is that we start with bounds on the RBP score that range from 0 to 1, because we've got no information so far. The first document in the ranking has a weight of 1 minus phi. It's just the way the geometric distribution works out. So we've got a weight of 0.2 at the top. And we say, okay, let's look at document number 7. And is it in the reference? And we go, yes, it's in the reference. Yeah. And we say, okay, we've now got evidence that the bottom score of the RBP range should increase by 0.2. And it's 0.2 because we've currently got a weight of 0.2, and we've currently got a weight of 0.2 because it's 1 minus phi because we're at document number 1. Then we advance. The weight decreases. So we've now only got 16% of the population looking at, in a normalized sense, 16% of the population. It's 80% of the population now, but it gets normalized down to 16 so that the sum works out as being 1. And we look for document 4, and yep, it's there. So the bottom score goes up to 0.36. You can see it changing at the bottom of the screen there. Document 11, we look for, it's not there. It's oh no. And that means the top score decreases by 0.128. And we've still got a range, right? Because so far we've dealt with 3 of the documents in the ranking. We've got 7 more known ones. And then, of course, we've got a dot at the bottom of the arrow there, which is, hey, the ranking keeps on going. It's a ranking. It's an ordering of the entire collection if we really want to push it that far through. So we've now got a range from 0.36 to 0.872 for the RBP score. And we keep on going, and I'm going to go a bit faster now. We missed another one. We found another one. We missed another one. We found another one. We missed another one. We missed another one. We missed another one. And we reached the end of the known prefix of the ranking. So what have we got? Well, we've got an RBP score that's, all we can say is that it's between 0.494 and 0.602. There's unknownness in that RBP score. And that unknownness is exactly, because we've got a geometric distribution, that unknownness is the size of it is known. It's just where the RBP score falls in that range that we don't know. The width of that interval has to be phi to the power of d, because that's a property of the geometric distribution. And so if we had more documents, if we had another 10 documents, we could refine that range and we'd get down to a smaller subinterval. These ranges are always converging, but there's always some uncertainty in the score until we've considered every single document in the ranking. So this is rank bias precision. If all of the documents down to depth D are judged, the score range at depth D is given by So rho is the residual. We call it the residual, and for a geometric distribution, the residual is easily calculated as phi to the power of d. And depending on the unseen documents in that tail, the final RBP score might be anywhere in the possible range. Now, phi is a description of a universe of users. It's an infinite number of users. If we have impatient users, so someone says, oh, we're not going to look very deep. A typical web user, for example, they all look at the first document, half of them look at the second document, a quarter of them look at the third document, an eighth of them look at the fourth document, and so on. So we've got very impatient users. If we do that calculation, we get this RBP score range. You can see it's actually quite a high score. It's 0.79, and it's also highly constrained. It's tightly bound. We get a small score range if we've got a small phi, but we can only have a small phi if we're willing to assume that our users are impatient. So this is where the user modeling is very important. You have to say something about what kind of users you think you're dealing with before you can work out how you're going to measure stuff. If we've got patient users here, people who on average are going to look at the top 20 documents, we get this kind of frustrating thing happening where the score range that we get out of RBP is so wide that it's almost useless. This score range, we couldn't set up an information retrieval experiment where we said, oh, look, we've measured 0.175, but gee, it might be as big as 0.774. Sorry, we can't really tell you. That would be unthinkable, right? But unfortunately, that's what we tend to do. It's just that we hide it without considering what the score range might be. The other important point to note out of this slide is that different user personas experience different things. Where we're measuring with rank bias precision, we're measuring what they experience across a population. And if we give them different parameters, they experience different things perfectly reasonably. So the parameter now genuinely is reflecting different types of user. Now, just as a bit of an aside about the experimental thing, what we ended up being able to do out of this work is say, hey, if we want an accurate experiment, we either have to have a low residual, or we have to have a low residual. And if we want a low residual, we must either have a small phi or a large d in judgments that run all the way down to d. And so we get this three-way trade-off. What do we want? Well, we want measurements that reflect user behavior, because if we're trying to measure a system, we want the measurement that we're generating to be reflective of what the users of the system are going to experience. So we want measurements that reflect the user behavior. We want measurements that are accurate, that don't have these enormously wide residuals where we say, well, actually, we don't know where it is in that range. We've got no idea. We can tell you where the bottom of the range is. We can tell you where the top of the range is, but we don't know where the measurement is in that range. So we want measurements that reflect user behavior. We want measurements that are accurate, and we want them to not, our experiments to not be too expensive in terms of QROS. And there's a kind of a complicated tension between those three things that it's easy to ignore, but RBP, if you calculate the residuals and report the residuals as well as the score ranges that you've got, will at least keep your eyes open to. You will know whether your experiment is giving you accurate measurements or whether you're stabbing in the dark. How do we choose the parameter? Well, we could obviously study a whole lot of users and say, what do they do? And we've done that with click logs, and we've done that with eye tracking as well to establish experimental parameters to fit in with the rank bias precision assessment. Or we can do it by thinking, and what I'm doing here is saying, what do we want to get out of an experiment, or what do we want to do? If we know a desired weight for the top document in the ranking, then all we have to do is choose phi equal to 1 minus W1, right? So we've got this way of choosing phi. But there will be some experiments where we want to bound the residual depth, either an upper bound to say we know the residuals below this value, and therefore we've got some control over the fidelity of the experiment. And there might be other experiments where we say, no, we want the residual at depth D to be at least that value so that we know that documents in the tail of the ranking are also exerting influence. So we can choose the parameter this way and say, look, we've got a desired residual at depth D, so the parameter is then dictated by that combination. But we can't actually, at least not with the geometric distribution, we can't target both. And I'll come back to that theme a bit later on in the talk. What do the curves look like? I told you, I threatened you with more of these graphs. Here's the RBP decay graphs, and the geometric distribution decays quickly. I mean, it has to decay quickly to have a bounded cumulative sum, right? So if we have a first document weight of 1/10, 0.1, then we have to choose a parameter of 0.9. The weights decay quite quickly. And I missed, not very good at doing this with my hand. The weights decay quite quickly, and very soon we're down into ridiculously small weights where the residual is going to be small. So we've got an accurate experiment. We can see that by looking at the cumulative sums. Here's the cumulative sum for 0.9. And by the time we get out to depth about 20, 30, we've got very, very small total residual. Remember, the residual is the distance between this cumulative line and the top of the graph. So we've got a small residual and we've got an accurate experiment. If we go for more patient users, so here's a user who on average is going to inspect 1,000 documents. And here is that user having reasonably strong weights on 1,000 documents. That's the 1,000 document mark there. And then it tails off after that. And the residual, it decreases steadily, but it's not small until you're getting into the vicinity of 1,000 documents. So there's a lot going on in that graph, but you can compare that with the DCG graph we had a minute ago. And that is the end of part one. That is measuring an observation that's a ranking in the context of a reference that's a set. I'm going to move on. I'm going to talk about ranking given ranking measurements because that's the next part in the story I'm telling you. So here's the picture. If both the observation and the reference are rankings, we've got a different kind of measurement going on. And typically for this, we use a correlation coefficient. We pull out our Python toolkit and we use Kendall's Tower or something like that. And what we want is for rankings, observation rankings B, that agree more with the reference ranking R to be assigned higher scores. And then what we've got to talk about is what agree means and what more means, because of course that determines what the measurement will show us. Applications for this kind of measurement. This first came out when we were talking about pruning heuristics, when we have an expensive computation and we've got a cheaper version of that computation. Maybe we're not looking at all the postings, trying to do a similarity score. We're trying to bypass postings. And so we've got a proper score that we're saying, this is what we should be getting. And this is what we're getting by saving 3/4 of the running time. How much are we losing? And so we've got a ranking that we want to achieve, the reference, the perfect ranking, the one that the complete computation would generate. And we've got a ranking that's our heuristic one that we're saying, gee, can we get close to this one and save computation time by doing this one? Okay, so that's the first use case here. Often we might want to compare systems and say, what systems are like each other? Who's borrowing from who? Who's subcontracting? Who's shipping queries off to who to get answers? And we can compare for a set of 1,000 queries. If we compare the Baidu rankings with the Bing rankings and the Google rankings, we'll find out which ones are closer to each other. And then here's one that popped into my mind last night while I was listening to Munia's talk. We get ranked lists of tokens, possible next tokens with probabilities attached to them, out of the inference of a generative model. And if we've got those lists, we can compare them with rank biased or ranking given ranking measurements. So there's 3 definite use cases in the information retrieval world, the web search world. And for all of them, we want top weightedness. I didn't mention that when I introduced correlation coefficients. Kendall's tau is not top weighted. If you've got a distortion at the top of the ranking and a distortion at the bottom of the ranking, they get given the same score, the same degraded score. But we want disagreements near the top of the ranking to count for more than disagreements down at the bottom of the ranking, because it's top weighted, it's a ranking. We've got some sense that the top is more important than the bottom. Because hey, these rankings go down to infinity. So there has to be zero interest at the bottom. They go down to the depth of the collection, which is effectively infinity. So what are we going to do? And here's the next part of the story. It's rank biased overlap. Rank biased overlap calculates the expected observed overlap between the two sequences when users, and wait for it, here's a little bit of memory. This is another edited version of a slide I showed you 10 or 15 minutes ago. We view the first pair of items and we say, what are we seeing? So we've got a user model. We've got a user who is saying, I will look at the first two things and I'll go on with probability phi and on with probability phi and on with probability phi, and eventually I'll depart. And what overlap do I see between the two parts of the rankings that I looked at? And then what's the expectation on that quantity across a universe of users that have the same behavior? And we just get a similar looking equation. It's actually just got the geometric distribution built into it again, and it's got what does this particular user observe as the overlap down to depth I, summed up as an expectation over all depths. So here is the definition of rank biased overlap, and this was published in TUIS in 2010, and it's had quite wide uptake, not just in the web search and information retrieval communities, but all sorts of communities where they're comparing rankings that might not be the same. We also have the idea of a residual still, because it's a geometric distribution. We can bound the tail sum. We can say what it's going to be in a mathematical sense. And so we get a sense of, have we looked at enough of the rankings yet to have an accurate measurement, or do we need to keep on looking or generating more of the rankings? The other thing that makes RBO quite distinct from things like Kendall's tau, not just because it's top weighted, because it doesn't require that the rankings be permutations. They can be anything. I can give you two disjoint rankings, in which case you'll get a score of 0 out of it. And if I give you two identical rankings down to depth infinity, you'll get a score of 1.00000. And if I give you a prefix of two identical rankings, I'll say, look, they're identical down to here. So the score is 0.99, but we don't know what's afterwards because you haven't shown it to me yet. So we've got a residual. So it's got all these same nice properties as we had with rank biased precision. And so here's the story so far. I told you I was telling a story. I started off with set versus set measurement. I went on and talked about ranking given set measurements. I've just very briefly sketched ranking given ranking measurements. And the amazing thing about this picture is that it took 15 years between rank biased overlap popping into mind and what happened just a couple of years ago. So this is the story so far. When I draw it like this, I'm sure you're all saying, oh, I wonder what's in that bottom corner. Oh, I wonder what's in that bottom corner. And if you're wondering what's in that bottom corner, why didn't you wonder it 15 years ago and beat us to the punch? Because what we're going to do now is look at that bottom corner. We're going to talk about set given ranking measurement, and I'm up to part 3 of the talk. We're going to fill in the bottom corner with set given ranking measurement. So here's the picture. If the observation B is a set and the reference R is a ranking, what should we do? And you're probably sitting there saying, here, oh, he's pulling our leg. If no one wanted it for all these years, why is it interesting? So you're asking, is this even a real situation? So I'm going to take a deviation and explain a situation where this isn't just real, it's very, very real. In a multi-phase retrieval system, we get queries being entered by a user, and they then get, I've just nuked that part of it. Oops. And they get given into a fast phase one, which gets us out a set, right? The first phase returns a set of documents. The second phase here then re-ranks that set to give us the ranking that goes back to the user. And so if we're trying to evaluate phase one, what is it we're evaluating? We're evaluating this set, this is the observation, and we're evaluating it relative to, well, we're evaluating it relative with what we would like to have there. And so that's a ranking. So what we're going to do now is say, okay, to measure the quality of the first phase of a two-phase system, we should be comparing it with the reference ranking R generated by applying the second phase to the entire collection. Now that's expensive. We don't want to do that in the production system. But for the purposes of quantifying the usefulness of a first phase, yeah, we can build a test collection. We can build a test collection by taking the expensive second phase, applying it to every document for each of 1,000 queries, getting 1,000 complete rankings of the whole collection, and saying what we want is first phases that give us the top of those ones. Okay, so it's a serious and interesting measurement application. And the observation that we're measuring is a set. And you're saying, huh? Can't we just use recall? That's what everyone seems to measure. Because like I said, this work only happened a couple of years ago. Well, here's a couple of examples why we don't want to use recall. So here I'm using recall at 5 to measure the quality of this set on the left. B is the set, the observation, relative to a target ranking of all of the documents. So I've got 5 things in my set coming out of the first phase, and I've got 10 things plus more, right? Because it goes ... at the bottom there. And this particular combination, if I'm measuring recall, I've got 3 things in the set, and if I go to depth 5, I get a set of 5 things out of R. And so recall is 0.6, right? So I've got 0.6 as the measurement there. And this one, you can kind of say, yeah, okay, I can see why it's 0.6. We've got 3 things out of 5 got carried over from the observation that are present in the reference. Now I'm going to go forwards, and then we'll go back again, and we'll do the optometrist thing where it says it's sharper here or sharper here. So I'm going to go forwards and show you another possibility. Here's the same ranking. It's a different set I've got over here. Here I've got 3 things in the set, document 11, document 7, and document 4. They happen to be the first things in the target ranking. And this time round, I'm also imagining I know where the 2 missing documents appear in the set. I'm saying, hey, let's have them in position 6 and position 7. But this is still 0.6 as a score. This is a recall score of 0.6. And so you have to ask yourself, is this set the same as going back that set? They overlap by 3, but look, I've missed out the top 2 documents, and I don't know where the other 2 came from. Here, I've missed out documents 4 and 5, and I do know where the other 2 came from. They came from positions 6 and 7. So I'm going to argue, and just rhetoric, right? You just have to believe me, or accept, or think about it and say, yeah, I believe that, because not just because he told me, but because what he spoke was truth. It's worse to omit R1 from B than to omit R2 or RK. And it's better to include RK plus 1 in B than include RK plus 2 or RK plus 999. It does matter which things are in the set, omitted from the set, and included from the set. It does matter. It makes a difference. So here we have rank biased recall, which is, like I said, something like 15 years after we thought we were finished with our rank biased work. And it's this formula. I'm not going to bore you with the details of the formula, but to note, it is the dual of what we had for rank biased precision. They are a partnership, right? It's got the same relationship to rank biased precision as recall and precision have, which is why it's appropriate to call it rank biased recall. And by now you're probably saying, oh, come on, what does it do? Well, here's those same two examples, looking at them very briefly. When I've got the three least interesting documents of the top 5 in the observation set, I get a relatively low score. And because I don't actually know the locations of the other 2 in the ranking, I get a residual range, right? So I've got a score range here for the rank biased recall score. And this is the worst possibility for recall of 0.6, which is what everyone until this paper has been measuring in these environments. Here's that other situation. Now I've got a rank biased recall of 0.606. It's got a much higher score, and it's an accurate score because we know exactly where everything is located. So we've got no room for uncertainty. We've got the locations of everything in B. So we've got a score range that is tight. So we've got an accurate measurement, and it better reflects what's going on. Does it make a practical difference? Well, can't have an IR talk without some experiments, okay? So here's some results from that paper a couple of years ago. This slide is blah, blah, blah. The thing that I want you to understand is that we took real systems and real runs and got 26,000 runs where the recall gave us 0.8. Okay, there's a lot of data in behind the graph. Here's the graph. If recall is 0.8, recall at 10 is 0.8, there are 2 things got missed out, right? 10 choose 2 is 45. So we've got 45 walking along the curve, bottom of the curve along here. We've got 45 sections where different combinations of 2 things got left out. At the top end here, the 2 things that got left out are documents 9 and 10. They give you the highest rank biased recall score. The ones down here at the left-hand end, the documents that got missed out were the first and second. You get low scores out of it. Remember, everything in this graph is a run that got a recall of 0.8. Then within one of these zones, there's 45 zones. Within one of the zones, if we walk along that curve, that's measuring what went in instead of the 2 that got left out. And at the top of the curve here, the ones that went in were documents 11 and 12. At the bottom of the curve here, the ones that went in instead of documents 9 and 10, that was documents 1,000 and 1,001 or something. Very low scores. And so we've got 26,000 observations here to show that recall isn't a very good measurement for this application. So does it make a practical difference? Yes, it surely does. And we're on to the something new part of the talk. And of course, a good story. Everyone lives happily ever after. So I couldn't resist putting they all lived happily ever after in here, though I suspect it's still not the end of the story. Something new. So here's a graph that I showed you a few minutes ago for scaled discounted cumulative gain. And I kind of critiqued it saying, well, the only parameter we've got here is the depth, and that has to be a parameter because the sequence doesn't converge. And it has very slow decay. So we get big residuals. We actually measure the accuracy of an experiment using DCG or scaled DCG. You don't want to know about it. It's just not reasonable. We had rank biased precision as an alternative that uses a different sequence. We get convergence, we get small residuals, quite useful small residuals, but it decays too quickly. And I also made the point that we've only got one knob. So with DCG, this graph, the one knob is the depth of the measurement. With RBP, the one knob is the phi parameter that the user, we're saying represents the user population. And so the question, this is a relatively recent question, maybe just 6 months old or something. What do we want, or what would we like if we could have it? What I would like is to be able to choose the top weight. Say, I'm doing an experiment where the first item in the ranking is this important to my final score. 0.2, 0.3, 0.05, 0.01. but I put a number on the first element in the rank, say the first one is that important. I'd also like somewhere further down the ranking to be able to say, at this depth, I want the residual to be this much. And you say, well, is that possible? And we've now got two constraints. So yes, it's possible. We just have to go to a two-parameter distribution. So we've got a two-parameter translated inverse power law distribution in use, where we've got an alpha parameter, there's the translation, and an eta parameter, there's the inverse power law. And provided certain, provided you say eta has to be more than this and alpha can't be negative, you end up with an infinite sum, which is what we want, which is bounded so that we can do this trick with calculating residuals and saying what actually happens. Now, in order to get us to the end of the talk, I'm not going to tell you the details of any of that, but I'm going to show you two graphs. Here are three different sets of parameters where what we've done is say we want the first weight in all cases to be 0.05. So at the beginning, this is a graph of residuals. We want the residual to be 0.95 at the beginning, but we want the residual here to go to 0.1 at 10 to the 3, and on this curve, 0.1 at 10 to the 6, and on this curve, 0.1 at 10 to the 9, and run the Python program, and it comes out and says, okay, here are the weight curves that you need. Here are the parameters that you need for the two-parameter inverse power law. And, well, the residuals go through the required points. And if you want to know more how I compute the parameters, you have to come to SIGIR 2026 in Melbourne, because this is work that will be presented at SIGIR 2026. So this is something new, and they all lived happily ever after. Time for my conclusion. It's time to wind it up. The story I've told you is a 20-year body of work that's led to a framework in which system measurement is viewed as scoring an observation B relative to a standard reference R, with B and R either of them independently a set or a ranking. And then using that framework, we've now completed the other three sides of the grid compared to the precision recall diagram we're all familiar with. And we've got rank bias top-weighted measurement approach for all of precision, overlap, and recall. We've filled in the grid. What I didn't tell you about rank biased centroids. I didn't tell you about rank biased fusion. I didn't tell you about rank biased alignment. I didn't tell you how to deal with ties on ranks. And I didn't tell you how to compute the parameters, but that's okay. You can find the relevant papers and read any of those. What I didn't tell you about more sophisticated user models. So this is a very simple user model. This is the first step in user models. And we've had another whole sequence of papers where we've developed the notion of users and their behavior to say, what does a population of users do if they've got this goal and these things that they're seeing on the way down through the ranking? And the most recent paper in that thread was at SIGIR 2022 in Madrid. I need to thank the Australian Research Council because they've given me lots of money over very, very many years, and I've just spent it going to places like Salvador and Brazil and so on. And the first half of that RB story was shared with Justin, who was at RMIT University at the time and is now at University of Melbourne again. And other papers in the sequence have been written with Paul Thomas, Falk Scholler, Leif Azzopardi, Peter Bailey, Joel McKenzie, Matthias Petri, and William Weber, who was a PhD student of mine and Justin. I've mentioned SIGIR. I took this screenshot a couple of hours ago when I was finalizing the slides. It's now 2 weeks and 3 days away. We're still taking registrations. If you want to come, please do come. And I promised you a revised possible title. Maybe I told you something you didn't already know about rank biased measurement in web search. And if you look very carefully, I've got the same shirt on. Finished.
Thanks a lot, Alistair, for a great talk. I really enjoyed it. And I especially appreciate the point about recall on the first phase of retrieval, because coming from the industry, I know how common it is to still use recall. And it's eye-opening to see the downsides that you pointed at and the potential fixes that can be applied. So thanks for that. We are now going to open it for question. You can go online and ask Alistair anything before I will. Or if you don't want to go online, use the platform and we will try to pick it up from there. So giving you a few seconds for a chance. Otherwise, I will start with my own question. Okay, so what I did want to ask, I have a couple of questions in mind, but I wanted to start, and it's a pretty broad thinking, but how do you think about rank biased measurement in the context of retrieval augmented generation, which is so popular these days, but doesn't really involve user behavior? Rather, we are interested in providing a context to a large language model. Do you think this is still relevant, or perhaps here we should go back to recall and precision types of measurements?
Yeah, I mean, look, it's a good question, and I'm kind of stuck in the past with this. I am thinking about rankings that are orderings of documents on a screen that have a direct motion. So another very common question is, well, what about shopping presentations where you've got a scan or image search and things like that? Yes, so retrieval assisted generation systems, you have to decide what that first phase is handing over. If it's handing over a set, then you've got set given something, and then you have to decide what's going to go into the second place. And if what you're looking for is a set, then you're back at recall and precision. But if what you're looking for is a ranking, then you've actually got rank biased recall required.
Great. Yeah, thanks a lot for that. And actually, we got the same question on our system. So I think, I think you just answered it as well. We will be happy to get more. I will ask something additional, maybe more specific. And you did touch upon it on more complex user models. I'm curious because you mentioned the rank biased precision published in 2010. Back then, I think, still the interface was mostly a web interface with probably 10 blue links or something similar. And then there was a huge move to mobile where, users are traversing maybe somewhat differently the results. Maybe, they only look at few results. Maybe there are maybe the phi type of parameter is too simplistic. Is there something interesting you've done during that time to account for such user behavior?
Gee, is there something interesting that I've done in that time? How long have you got? So
Yeah,
one of
only
the
2
things we
minutes,
did
unfortunately.
was eye tracking experiments, admittedly in a 10 blue links environment. But one of the things that we discovered with the eye tracking was that, and maybe that everyone understands this, is that it's not a forwards progression one at a time, the way that the rank bias precision models it as being. It tends to be a down, return, down, return, down, return, down, return, because people are anchoring one of the documents and saying, that's the one I'm keeping in mind. Is this one better or worse than that one? Oh, yeah, this one's better. And so they re-anchor and then keep on looking. And then eventually they click one, right? So we had these conditional move tables in a paper in 2013 or something, where we were saying it's not just what documents got looked at by the user as a cumulative mass over a whole lot of users, but what jumps do they make? And so a jump of +1 was often followed by a jump of -1 in their fixation. And then a jump of +2 was often followed by a jump of -2. So they were referencing something and anchoring on it, going 1 down, going back, going 2 down, going back, going 3 down, going back, and then advancing. Okay, so that's a non-linear sequence. And then my claim about the user model reflecting the benefit that the user gets is no longer true. And then to go back to the shopping interface, if I mean, we've all seen the heat maps of people looking at an image display of the strange jumps that they do. So there's a kind of a multitude of linearizations possible, and each of them you'd have to say, well, what's the probability of a user following this path, and then what's the score we will give to this path? And as an expectation over an infinite number of users, if you've got a probability distribution, you can calculate the expectation. So some of the ideas are the same, even if the detailed implementation is different.
Very interesting. Yeah, thanks a lot. We are at time, but there is an interesting question on the poll, so I'll quickly ask it as well. And it is regarding the relevance, the judgments that it is based on. So does it make sense? Does it make a difference if relevance judgments are coming from machine and not from humans?
Yeah, good question. Does it make a well, I'm going to give a slightly facetious answer first. Does it make a difference to me? No, not especially, because if you regard them as being judgments, you can use them. So then we're back to the more primitive question of, does an LLM make good judgments? And that's a question that's had a lot of work done on. And I think the conclusion is you give it the right prompting and the right care, it makes judgments that are as good as crowd workers and maybe even as good as experts. So does it make a difference? It's hard to say it's going to, but all the same caveats. You've got to use a different system to do your judgments as you do to get the document rankings in the first place, because otherwise you get a self-reinforcing, you're just in a habit. You're being told, yes, they're the ones to have at the top because I put them at the top.
Right. Cool. Thanks a lot, Alistair. This was again a great experience. And yeah, we'll see everyone in half an hour for the
Can I just
session.
ask the host how many people we've got online? Just that curious. The host has already gone to the morning tea break.
Right. But we should get an answer and we will share it with you, Alistair, later on.
Sure, I'm curious to know.
Not say in the bar.
And still taking registrations for Sagaya.
Right. For 2 more weeks. Please do. Thanks a lot. Thanks, everyone, and we'll see you soon.
Bye.
Bye-bye.
All right, I think we're out.
Thanks a lot, Alistair. Yeah, I think we are not on air now. Yeah, I really enjoyed it. Really basic